Welcome back. Today we talk about energy storage, part 3. Still chemical and electrical types of storage, but today we'll talk about lead-acid batteries, lithium-ion batteries and supercaps. So first let's start with the lead-acid battery. Lead sulfide acid batteries, also called lead-acid batteries, were invented in 1859 by the French physicist Gaston Planté. They are still the most commonly used rechargeable batteries in the past, at least for high capacity requirements. The latest development is that the lithium-ion batteries, which I will treat next, are pretty much keeping up or overtaking the use of lead-acid batteries. While the energy to volume ratio is acceptable, the energy to weight ratio is rather low compared to other battery types. They are relatively cheap and can supply high surge currents. Each cell has a nominal voltage of 2 volts, which can be increased via series connections of battery cells. The principle, so the 2 electrode plates, one consisting of pure lead and one with a lead oxide surface, are in an electrolyte consisting of thinned sulfuric acid, typically in a density of 37% of sulfuric acid. During discharging, both electrodes turn into lead sulfide and the electrolyte turns into water. Therefore, discharged lead-acid batteries can freeze. So here, this is direction. So lead sulfide and lead together with thin sulfuric acid turn into lead sulfide and water. The other way around, during charging, the lead sulfide on both electrodes is converted back to lead oxide and sponge lead. Turning back to lead oxide, PbO2 at the positive electrode and lead at the negative electrode. And the sulfide ions are driven back into the electrolyte solution to form sulfuric acid. Typically for lead-acid batteries are automotive batteries. They are also called SLE batteries for starting lightning ignition. They are designed for short time, high output power and not for deep cycling. However, this type is often used for solar application and is relatively inexpensive and easily available. The lifetime is relatively short, 1 to 4 years. The maximum DOD, that means depth of discharge, should be not higher than 50%. Seasonal storage is difficult with this kind of battery. In order to avoid acid stratification and therefore sulfitation, the battery can be charged at the gathering potential, so higher than usual for a short time, or charged directly with a charge controller by the photovoltaic generator from 2 to 5 minutes twice a week. Mechanically shaking of the battery does not help a lot, as the spacing between the plates is too small to ensure remixing. Industrial batteries. Industrial batteries are used both for traction and stationary application, yet mainly for cyclic applications. This is possible by using thicker plates and tubular electrodes. This active mass in the tubular type is armed by a plastic protector in order to avoid mass shedding. The tubular type is often used also for solar application because its specific kilowatt-hour costs are relatively low. Specific solar batteries. These special batteries are derived from the SLA batteries and the industrial batteries by improving their cycle behavior. Many battery companies adopt modified SLA batteries as their basic technology and is therefore relatively inexpensive. The main disadvantages of the normal SLA battery, namely bad cycling behavior, can be reduced by using thicker electrodes, using electrodes enclosed in special pocket separators, thereby avoiding short circuits by shedding of active mass, using an excess of electrolyte, thereby decreasing the drop of acid concentration during discharge, using grids made of low antimony and antimony-free alloys, thereby reducing gassing and self-discharge. Here you see the self-discharge at different operation temperature. On the x-axis you see the idle times in months, and here you see the remaining capacity. So at the beginning, month 0, all batteries are fully charged. Tropical climates, and you have, for example, here 30 degrees of operation temperature. After 9 months of idleness, the battery has only a remaining capacity in the vicinity of 50%. Here the lifetime as the function of depth of discharge, or DOD. You see there's a huge difference between industrial batteries and consumer battery. This is also represented in the very different price. So consumer batteries, if you have a high discharge, for example here 50-60%, lifetime is very short, so in the vicinity of 300 full cycles. That means after 1 year they are degraded. For industrial batteries, this looks much better. If you have a depth of discharge of 50%, lifetime is in the vicinity of 2000 cycles, so that's in the vicinity of 6 to 7 years. Reduction of lifetime at high operating temperatures. So you see here the lead acid battery with the red color. So you see at high operation temperature, the lifetime is drastically reduced. For example, if you go from 20 to 30 degrees, you have only 50% of the lifetime. If you go even further to 40 degrees, then it's only 25%. As a rule over the thumb, you can say with the increase of temperature by 10 degrees, you shorten the lifetime by 50%. Nickel-Cadmium battery, here in blue color, is more resistant, but it doesn't play a big role anymore. Here you see the speed of discharge and operation temperature. If you discharge a battery very quickly, then the usable capacity is reduced. So you see here, if you discharge, for example, within 5 hours only, you have a usable capacity in the vicinity of 70%. If you use colder batteries, like often in car batteries in the morning, then the usable capacity is even reduced. It doesn't affect lifetime. Contrarily, if you have higher temperature, then lifetime is shortened, but capacity is increasing a little bit. VRLR batteries, maintenance-free batteries. Usually when batteries are overcharged, they produce hydrogen, and there's a consequential loss of water. You have to refill that water with distilled water. Sometimes it's a problem to get distilled water, and you have to have some reliable person who is doing that in a regular way. And sealed units, they minimize that loss, so the hydrogen and the oxygen cannot escape. Then sometimes you have some catalysts who allow a regeneration, and therefore it's called maintenance-free. But a well-maintained open batteries has a longer lifetime than a VLR battery. This has been to reduce the effect, so the oxygen being developed at the positive electrode is transported to a negative electrode and then reduced back to the water via a catalyst. The cost of the batteries as a function of capacity, you see here, very small batteries are quite expensive, so mid-size are the cheapest one here, so in the vicinity of about 100 euro per kilowatt hour. When you come to industrial battery, they usually are not so often sold as, for example, car batteries, and they are a bit expensive. Only if you go to a very large size, you have here some price reduction. Nickel-Cadmium batteries, they have some advantages over lead-acid batteries. So they have a higher energy density than lead-acid batteries. They can be fully discharged, so lifetime is not suffering so much from discharge. so they don't need to be oversized. They are more rugged, and they have a much better temperature performance. They have a lower internal resistance that permit high currents. They can also more quickly charge and discharged within 30 minutes. And also they maintain a relatively uniform voltage during discharge, and they have low maintenance requirements. They have also some disadvantages. They are typically 2 times more expensive. They have lower energy efficiencies. While you have 80 to 90% at lead-acid batteries, here at nickel-cadmium batteries it's only 75%. You have this memory effect. So contrary to the lead-acid batteries, which you shouldn't cycle so much, they need sometimes cycling to avoid the so-called memory effect. So if you only cycle about 10% of the possible discharge, the battery thinks that it has a reduced capacity and it's not able to discharge any deeper. And this is called memory effect. Therefore, they have to discharge once in a while to zero. The cadmium is a hazardous material, so it is important to make sure that the battery is not disposed but recycled after usable lifetime, but the same applies to lead also. Let's come to the most modern battery, the lithium-ion battery. How does a lithium-ion battery work? So we start with the history of the lithium-ion battery. We spend a bit more time for the lithium-ion batteries because probably it will be the only chemical battery that will survive. Or there will be a complete other technologies, but I don't think so at the moment. The second chapter is here, the lithium-ion battery as a rechargeable battery. First, for the primary cell, this is non-rechargeable. Then I will discuss a little bit about the process of charging and the discharging. How does a lithium-ion cell work? The range of materials for electrodes and operation properties, the share of costs. So how can we possibly make a lithium-ion battery cheaper? What's most expensive? Is it material, or is it processing costs, or labor costs, or energy costs, and so on? Discussed here. And the perspectives. Let's first go into history. Lithium-ion battery as a primary cell, so as a non-rechargeable battery, is quite old. So it's been used since the 60s for space and military applications. In the 70s, it's also been used in computer technology for permanent storage, for internal clocks of computers. Since the 80s, they are used for consumer application, so bottom cells. You can even buy them in supermarkets, so micro and micron cells or 9-volt blocks. They are usually more expensive, but lifetime is much longer. So for example, if you have fire alarm monitors, usually they have lithium 9-volt blocks. Advantages, they offer a single cell high voltages up to 4 volts compared to 1.2 to 1.5 volt at conventional battery systems. They have a high specific power and energy density of 300 to 400 watt hours per kilogram. They have hard characteristic of discharge. That means that the voltage stays constant for a wide operation point. It means also at a high discharge level, or if the battery is almost empty, you still have the full voltage. You have a wide temperature range of operation, so specifically at low temperatures. And you have a low self-discharge rate, so you can storage a possibility of about almost 10 years. Come now to a rechargeable battery or secondary battery. This history is much younger. In 1980, Professor Goodenough from the University of Oxford has proven lithium cobalt dioxide is a suitable electrode material. And together with Mr. Mantiraman from the University of Texas, he showed that the electrodes that contain sulfates, they provide a higher voltage than the formerly used oxides. Interestingly, in the same year, there was a patent by the German Peter Busch on a lithium-ion accumulator, including he presented a prototypes, but there was no interest by investors in industry. Independently from that, Sony and Asahi and Kasai, they manufactured their own lithium-ion accumulator without considering that patent. In 2002, there was another step in lithium-ion history because the electrolytes, the liquid electrolytes, have been substituted by polymer foils. So you don't need any containment anymore against liquids. So you just have to use a foil pile. So it's much more easier to fabricate, and also you have a lower weight. Let's take a look at the functioning of a lithium-ion battery. So first we take a look at the discharge condition. So we have two electrodes. While it's discharged, we don't have any positive or negative. It's completely discharged, even short circuits. So you have here copper electrode, and there's a lattice of carbon, graphene here, C6. And on the other side, you have lithium cobalt dioxide here. So the lithium atoms are the smallest. Then you have the oxide, dioxide, which are relatively small, and the cobalt atoms. It's not necessary cobalt. You can also use manganese, nickel, or even iron. We come to this a bit later. So now we start charging the battery. So we supply electrons here to the copper electrode here, and we take away electrodes here from the aluminium electrodes, and we take the electron away from the lithium atoms. So we have here lithium ions here positively charged because we took away this electron and get them here. So there's negative charge here. So they try to go to the other electrodes. We have a separator in between. It acts as a filter. So the size of the holes in the separator have exactly the size that the lithium ions can pass and the rest not. And if we continue charging, so this is a chemical formula for that. So we have a cobalt dioxide and the lithium ions and electrodes here. You can do it also multiple times, therefore it's in X here. So it's not necessary that you just only do one ion and so on. You can do multiple of those. On the other side, you receive an electron here, and this combines with the lithium ion to lithium, and it's stored in the carbon lattice. Just to mention, you can also use other materials, as I mentioned, also manganese and so on. So the formula looks a bit different, but not very, but the principle is the same. Here we have now the condition of 100% charged lithium-ion battery. So there's almost no lithium anymore on the anode, all on the cathode here, and we have here the stored lithium. The lithium atoms are not anymore ions, so they are in this carbon lattice. So we start to discharge now. So we have here a supply of electrons here, and they go in that direction. So if we take away electron from the lithium atom, it turns into an ion, and this ion is transported here because there's a negative charge here through the separator to the anode. This is our load here, and this is our current meter. So just ampere meter load, and just we discharge. If we charge, we need a source, but here we don't need a source. So here again the formula. So we have here the LeC6 turns into lithium ions plus the old lattice of carbon plus an electron. And here we get an electron, could be also multiple, as I mentioned already, and turn back into the original condition that is set. So how are the lithium ions stored in the carbon grid or carbon lattice? It's called intercalation. It's a bit different from a pure chemical reaction. It's a bit less than a chemical reaction. Why it's not a chemical reaction? Because it doesn't significantly alter the structure during the process of incorporation and removal. So this structure looks still the same before and after the charge or discharging process. So they are just embedded in the carbon lattices and redeposit later. You see, go in and out, and they don't change anything. It's almost like a conventional electrical capacitor. Here you have this lattice, so there's graphene layers and so on, and you have to design them adequately so they are able to store these lithium atoms. What is a separator for? It serves for the mechanical and electrical separation of the electrodes. So it's a kind of filter which lets a lithium ion pass, but not the electrolyte. You see that, so the other atoms cannot pass, only the lithium ions. Usually it's designed by polyethylene or polypropylene foil, which is initially has a thickness of 15 to 25 micrometers. Then you stretch it during heating up, and then you create some holes, so you create some porosity. If it's done in a very defined way, you can create exactly holes in the size you need. Also, it serves against short circuits, the growth of so-called dendrites. So these are like dripstones by the accumulation, by the inhomogeneous accumulation of lithium atoms, which may happen if you have a very high current or if the manufacturing of the battery is not done in a homogeneous way. I'm sure if you have a dripstone that leads to the other electrode, it creates a short circuit, and it can even lead to an explosion of the battery. So you want to avoid it, therefore the separator is quite essential. In short words, the cell reaction of a lithium-ion battery is based on a very reversible lithium-ion storage reaction. The electrolyte is an inactive material and so can be mentioned minimum in size. The thin electrodes that are piled and wrapped together with relatively high voltage levels allow high energy density. Energy density is described here. Just one parameter is the voltage, and here you see the difference here between the electrodes, the voltage difference. So usually you use here these materials in blue and the one in reds, and so you are sure that you have a high voltage difference and therefore a high energy density. Here are some examples here from materials. We discussed the first one. Lithium cobalt dioxide has a difference in electrical potential of 3.7 volts. Its theoretical energy density of 518 watt-hours per kilogram. Accordingly, you have for the negative electrode this graphite LiC6, what we discussed here. Okay, the neglectable difference in electrical potential. Also, specific energy is quite low, but you can think about different materials in order to increase it. But these are own prototypes only, and also if you think about germanium, this is rather expensive and not available everywhere. So this is also, you know, some of these manganese, this is often used, so this is a higher voltage but lower specific energy and so on. To come to here, this looks quite promising, nickel-cadmium oxide, and so lower voltage, but here a higher energy density. Depends on the different parameters, and so I don't want to go into details. Here are some axes about future development of lithium-ion batteries. So you see here, that's from 2010 here, but still this didn't change a lot. This is from the Berger Consulting in 2010. You have here the different developments, and so in the future, 2020, higher specific energy densities. The light blue one is for the battery pack, and the dark blue one is for the single cells here. During this study, there was also made a cost share. Usually, this information is quite secret, so I couldn't even find any new one, but still it gives you a hint how the costs are divided. So you have here the cost of the raw material. This in total costs about $500 per kilowatt hour of battery storage. Nowadays, it's $150, even rumors are saying that $100 per kilowatt hour already reached. So this was a decade ago, so it was quite expensive. Maybe the distribution is still the same, so there's 17% of raw materials, 22% of the material processing. And here you see the material cost split, so most is for the cathode, 13% for the anode, about 14% for the separator, for the electrolyte 9%, and for the other material, copper foil, aluminium foil, for the electrode material, binder and hardware. See depreciation, that means that the machines you used for manufacturing are getting old and you have to invest new ones, and this is called depreciation. Direct labor, energy doesn't take so much overhead. So margin, this is a profit, and this is a development of the battery. So this is a cost development here. by Bloomberg in 2019. So you see here in 2013, the cost of a pack of batteries still have been in the vicinity of $650 per kilowatt hour. So the cell costed about $446 per kilowatt hour. So this probably was also cell costs if you saw this former. So this was, yes, it's a cell costs here. If you go 3 years before, it is quite feasible that cell costs are in the vicinity of $500 per kilowatt hour of cell costs, but you have to interconnect them in series and encapsulate them and so on. This is this cost, and together, even in 2013, was $650. 2 years ago, this cost decreased a lot, so cell costs are only at $127 per kilowatt hour. The pack making is $49, and altogether $176. And this is a German research, and they even estimate that this year we have costs in the vicinity of 108 euro per kilowatt hour. So what is about $120 per kilowatt hour for the whole, not only for the cells, for the whole battery. Quite important is how you treat the batteries. A first significant example is you can discharge theoretically the lithium-ion batteries quite deeply, so they don't suffer such an extent of reduction lifetime as lead-acid batteries, but still you have to consider some issues, and this I will discuss with you in details. This was from a PhD thesis from Mr. Kai Ries from the University here of Aachen, quite new one. So he shows here first we will see the so-called calendric aging. So you don't do nothing, you keep the battery stored, and you see what's the available relative capacity after the storage. They have a quite interesting result. If you store the battery fully charged, it happens because people are used to do that from the lead-acid battery, so they always keep the battery fully charged, or the notebooks are always connected to the electricity supply, or so do the cell phones. And you see that's not very favorable. So just by this storage, you reduce significant amount of relative capacity. So much more recommendable if you keep them stored at a relatively low state of charge, SOC. So that's more recommendable if you keep them charged. It's not so recommendable to discharge them totally, but some amount is quite recommendable here. This is very different to the lead-acid batteries. This is now the degradation of lithium-ion batteries as a function of temperature. So you see here at all batteries, so lifetime is longer. So this is a number of days, but this is proportional to the numbers of full storage cycles. You see here, if you keep the battery cool, lifetime is really, really long. If the battery is warm here for 60 degrees, lifetime is really shortened. Also, if you charge your battery, for example, your cell phone very quickly, you feel that it's getting warm, and that's not recommendable because it will reduce the lifetime. If you charge it in a more slower way, the temperature stays lower, then a lifetime is much higher. Here now is something interesting. So the way of cycling, so this is delta SOC. That means here, for example, the blue curve, that you mean you always use a full capacity, you always do a full cycle. So you charge the battery fully and discharge them completely. Average between 0 and 100 is 50. And then you see this blue line, lifetime is really short. So this is not so recommendable. If you charge your battery more often, for example, if you just use 20% of the capacity, so you, for example, medium is here 50%, that means that you charge them to 60% and discharge them to 40%. So you have a delta SOC of 20%. And if you follow that curve, you see that you have a lifetime which is about 3 times as long here. So this also, if you treat your cell phone battery, not always fully charge them. So it's always good to keep them in a medium level, charged and discharged. Here, this is as a reference. If you don't use the battery at all, this is not realistic. But here you see that at best if you have only 5% of charge and discharge. So you just cycle it from 52.5% to 47.5%. Here the cyclical aging, so the importance of the SOC level. So as I mentioned, if you keep it medium here, you have the best lifetime, so you always keep the battery operating in the medium charge state of charge here. This would be the red line. If you keep it at a very low charge level, lifetime is very short. So you see there's a blue curve that is very, very, very low state of charge, and this light green line is a very, very high state of charge. So recommendable is this line, and that means we always keep the battery medium charged. Last but not least, we come to the electrical storage, the so-called double layer capacitors or ultra-capacitors. These consist of electrodes that are surrounded by electrodes. If a voltage is applied, ions accumulate at both electrodes of inverse polarity, like a conventional electrical capacitor works. The energy is stored in the form of the electrical field on the electrodes and the ions of the electrolyte in between the carriers. The electrode with the dielectric behaves as two capacitors connected in series over the electrolyte. So you see here this one. So you have here this is the electrolyte. This is the fixed electrode here, and this acts as a capacitor because here we have the negative, the electrons, and here we have positive charges, and here's vice versa. So this is actually like two capacitors interconnected in series here. Here also you have a separator similar to the separator at the lithium-ion battery. Again, here you see temperature influence. So here, life in months, here you have a very long time of this battery, and if temperature goes up, lifetime is very much reduced. And so is the applied voltage for the supercapacitor because they destroy the electrolyte. So they are very sensible against overvoltage. So best keep them at this here 2.3 volts rather instead of 2.5 volts. You're sure you have a higher energy density, but the lifetime is significantly reduced. Here is a data sheet of a typical ultra-capacitor by the company Maxwell in 2016. This company has been recently brought up by the Tesla company. So you see here the rated voltage of that specific capacitor is 2.84 volts. This is a really high capacity, typically 3.4 kilofarad or 3,400 farad. This was some decades ago was really impossible. So the 1 farad was really high value, and most of the purchasable capacitors, they have the best ones, electrolyte capacitors, they have vicinity of 600 microfarads. This is that you have farads or even kilofarads is was thought as an impossible thing. This is the internal resistance, so this determines how fast you can discharge them and how big the heating up is. If you have really high discharge rates and if you have a high resistance there, then you have a considerable heating there, and this may destroy the capacitor. So if you have just a 0.28, so it's really low, so you can really supply a high discharge current. Here you have a specific current, so 6.7 kilowatt per kilogram, and so on, 8.5 kilowatts. And here there's all this data given, temperature resistance, and so on, what else. Yes, projected lifetime 10 years. This depends really on the temperature and the voltages you apply then. Absolute maximum current here 2000 amps, that's quite a lot. So a permanent membrane as a separator between the negative and positive electrons to prevent a short circuit. A storage capacity is determined by the size of the membrane, so the area of the membrane and the distance between the membrane. And at the same membrane and the distance between the electrodes. So the thinner you can make the membrane, the higher is the capacity. And the active porous carbon materials are mainly used as materials for the electrode with a large surface. Yes, as I mentioned already, they are often called supercaps or ultra-caps. They have a very low, so this can provide energy very quickly. The range from 0.5 farads to about 5,000 farads. We saw just this typical device with 3,500 farads. Energy density is quite low, 4 to 5 watt hours, not kilowatt hours, but watt hours per kilogram. And yes, you can vary from cylindrical to rectangular shapes. The energy stored in a capacitor is half. Then as you see, this is a capacitor the capacity here given in farad, and then the voltage in square, half of it. So they are suitable for applications where loads require a high number of short charge and discharge cycles. For example, you could apply them for acceleration and recuperation in cars or buses and trains, or for stabilizing the voltage in electrical energy systems. They are often used as a battery supporting application, for example, as an emergency power supply for the blades of wind power that have to be turned away from the wind during a failure. Yes, as is mentioned before already, they also can call it slip control. So this is some applications on that. The decisive advantage is their high power density, not energy density, power density, and thus delivering high amounts of power over a short period of time. Furthermore, the advantages include the high efficiencies, 90 to 95%, high cycle durations and reliability. The disadvantage is that they are very sensitive to overvoltages. You saw this graph here, so if you just increase voltage a little bit more, then lifetime is drastically reduced. Also, you saw by the formula here that the voltage changes with the state of charge, very contrarily to the conventional chemical batteries, which has a so-called hard characteristics. So even if the battery is almost completely discharged, the voltage almost stays the same. Here not. So if you discharge it, voltage goes down significantly. In comparison to other batteries, they have a very high self-discharge rate, which is in the vicinity of 2.4 to 10% per day. So they are not suitable for long-term energy storage. So the efficiency is quite good, 90 to 95%. Power available in some stacks or some so-called modules, from 30 kilowatt to 3 megawatts. Storage capacity is 5 megawatt hours, playing up to 120 megawatt hours. So in general, it's not very impressive, but for these short-term capacitors, it's quite a lot because you can have high power delivery. Energy density is relatively low. Discharge time is quite fast, not only 1.5 seconds, you can do 10 times faster. The self-discharge rate is really high, but the number of cycles is really high. Specific investments is quite high. Not sure whether these numbers are correct. It should be even higher than that. At the very end of the lecture, I still want to discuss about the storage technologies in overview. So we will have here the capacity on the x-axis, on the y-axis here, time in hours, the discharge time. And so you see here for very short time available, you have your double capacitors, what we discussed in the gray color, or you can use a flywheel as a mechanical storage or conventional batteries. If you want to go to a longer term storage, as we mentioned already, compressed air storage, or here in dark blue, the pumped hydro storage power plants, or here the renewable power methanes. If you want to use the long-term infrastructure, you will have some additional losses, but here you can have a very high storage capacity and also can store it for a very long time. If you use hydrogen only, it's a bit reduced. And here thermal energy storage can also use, but you have to make sure that the conversion efficiency back from thermal energy into electrical energy is quite good. Usually this is quite limited by the temperatures and the Carnot efficiency. Here again, another representation, very similar to the one before, but by another source. This seems to be newer, at least the year 2016 is mentioned here. And here this PTG, power to gas, it's called here synthetic natural gas. It's power to gas, pumped hydro storage, compressed air storage, batteries, and also flywheels, and those capacitors, supercapacitors, which we discussed. This is just under development, superconducting magnetic electrical storage, so I'm not aware of any prototypes or even things on the market. So these are the application here, what you have here. So energy management here for just with the highest power and discharge time, as you saw before, is pumped hydro or compressed air storage. this power to gas and so on is not mentioned here. Just the conventional types of batteries is in particular the chemical batteries. And if you go to supercaps and so on, so you have a very small discharge time, and this serves for a short period of UPS, means uninterruptible power supply. You can use for that, or just short-term power supply and so on. Here, if you have lead-acid batteries, they can work longer. Nowadays, it's a bit older, so you have here, I think it's from 2009, lithium-ion batteries. They are also suitable to have high system power ratings. Here you have the volume density and the weight density here, so kilowatt hours per ton and kilowatt hours per square meter. So this is particularly important for mobile application. So this is from the point of view for the utilities, what you can do that with the different kinds of storage. So here more power, more storage time. So here commodity storage over a long time at high power. This is T, and D means transmission and distribution. Facility deferral. If you have a lot of storage, you can avoid investments in additional transmission lines because you can balance the use of a transmission lines, so there are no peak loads, and so you smooth the load over the transmission line, and so you can avoid some investments costed by that. Here, all the green part is renewable energy management, that as we discussed now. Here's the other applications: power quality and reliability, frequency control, and so on. Here, voltage control is also an issue in this power and duration length, duration range. Here you see the lifetime of the different options here. Longest lifetime have flywheels. All the mechanical parts have usually a quite long lifetime. The chemical part have a bit shorter lifetime. Also, energy efficiency is highest at the capacitors and flywheels. Pumped hydro, as I mentioned already, so from 70 to 80%. Compressed air is usually significantly lower. These are the costs here. So first you have the capital costs, investment. We said here what much you pay for the battery, but here it's also considering the lifetime and cycles and the conversion efficiencies. And here you see the options of pumped hydro is here still the best. This is an overview of all technology. So you have here the different technologies, starting one with pumped hydropower, going to 8 number redox flow batteries, and then you have the relative costs of that technologies, the costs per cycle, the response time, the major maturity. For pumped hydropower, this is very mature. Some other technologies, for example, here, if you take a look at lithium-ion batteries, it's semi-mature, so not completely new, but not completely mature as stationary big batteries and so on. And then you have the conversion efficiency as a parameter, the daily self-discharge, and just in a nutshell, the summary of that technology. And then you have here the different application. So where is the storage needed in the grid or transport and so on. And here you see the different dots here. This is one means just seasonal storage. Here you can use either pumped hydro storage or number 5, hydrogen storage, and so on. So you can take a close look. Finally, I give you some hints on literature and resources. Quite extensive books, a Handbook of Energy Storage by Mr. Sterner and Mr. Stadler here. It's a new edition from 2019. The hints I gave you for the lithium-ion operation, this was from a presentation by Mr. Kai Ries from the University of Aachen here. You can find it under this link. This is a PDF file of that talk. There are also some other technologies, some other books. Some of them are a bit older, either lead-acid batteries or supercaps and so on. You find here in this literature review here. So that's it. Thank you very much. There is now just an exercise here, and I will discuss quickly the exercise to be made. So here, our first exercise is here. You should compare different storage technologies. So first, you have a household in the tropics that has the following consumption during nighttime. So you have here a refrigerator of 50 watts that runs permanently, so 24 hours a day. LED lights of 4 watt each, about 10 pieces, and they run from 6 p.m. until midnight. A TV set of 150 watt power. It runs here for the telenovela from 8 p.m. to 11 p.m. You should first find out which option is the cheapest if we compare to different battery technologies, two different battery types, they are same technology. First, we take a cheap automotive battery that's available for €150. It has 12 volt and 150 ampere hours. If you would discharge 100%, we just only consider a discharge of 50%, otherwise lifetime would be really very short. So we consider 50% of depth of discharge. This would have a lifetime of 1000 cycles. If we go to 70% of depth of discharge, we only have 500 cycles. Output voltage is 12 volts. Charging voltage is 13.5 volts. And then the so-called Coulomb efficiency, or other words, ampere hour efficiency, is 0.9. As a hint, this is not the energy efficiency. Second option, we would compose an industrial battery. We only buy 2 volt cells and interconnect them on your own. So a 2 volt cell is available in blocks of 200 to 1000 ampere hours, and it costs €200 per kilowatt hour. It has a lifetime of 3000 cycles at 50% depth of discharge, and a lifetime of 2000 cycles at 70% depth of discharge. The output voltage is 2 volt. The charging voltage is 2.4 volts. Also, the ampere hour efficiency or Coulomb efficiency is 0.9. So if we should consider that's not the energy efficiency. So how much does 1 kilowatt hour in a storage cycle energy costs? And in total, including a PV generation, costs of 10 cents per kilowatt hour. For costs, we use the abbreviation small, so specific cost small k. For absolute costs big K. Here the small as specific cost of PV is K with an index of PV. It's 10 cents per kilowatt hour. So part 2. Now we equip that refrigerator with some phase change material, so for example ice and so on. So we can use this ice as a thermal storage. So we don't have to power it at nighttime because it stays alone at the low temperature, at least until all the ice has been melted. This allows that the temperature stays at the desired temperature during nighttime. During the day, the refrigerator and the PCM are usually operated directly by PV at costs of also 10 cents per kilowatt hour. The charging and discharging of the PVM in a cycle has an efficiency of 60% in total. The question is, how much is the maximum price of the PCM equipment in order to be still competitive with the cheapest battery option? Lifetime of the PCM system is estimated to be 10,000 cycles. If you would have just ice, and there's no limit of 10,000 cycles, but some of the materials, the PCM materials, they are paraffins and they have a certain limit in lifetime. Okay, that's already a solution we discuss later then. Thank you very much. This exercise is also quite extensive. So take your time and try to solve these.